Huh?
I know I was not here.
I like your shoes, too. Those are cool.
We got some homework to show me, so let's go ahead and get that out.
What is everything? It's just like 4.3, right? Mm-hmm. You decide where you want to school yet? You're going where? Where's that? Are you playing golf? That's cool. Probably Lisa McRae. It's in Bannerville, right outside of Boone. How many more units do we have? How many more units do we have?
Till we run out of time. Till we run out of time.
Okay.
We can do as many as we can, Kel. I fully anticipate that we will get farther than what we did last year, because I won't have to take the better part of 4 weeks off in the middle of the course. Now, that being said, I can't just definitively say we're going to get this far or that far. I know for sure we will absolutely get past Unit 5, which is where we ended last year. How far past Unit 5, I do not know. I would like for us to get all the way at least to Unit 6 or 7, which would be just about halfway through the curriculum that you're supposed to get through. Okay? We'll wait for our other troublemaker to come along here. Fam, where you been? You couldn't have set your stuff down first? Okay, well, that's reasonable. Get your homework out for me, please, sir. Thank you.
Pretty good. We went to the doctor on Tuesday, and it's just a sprain, but I only have to wear the brace until the end of March.
I'm looking 4.2 and 4.3.
I just said 4.2.
No, that's cool.
Okay. So let's talk about a couple of things here before we get started. First and foremost, got parent-teacher conferences coming up this week. Now, as I've met many of your parents once or twice or 3 or 4 times before, I imagine that there won't be super much to talk about. But if they want to be there, of course, by all means, you're more than welcome to. We can sit down and talk about how you're doing. Most of you doing pretty good. Maybe not as good as you're used to doing, but it is AP calculus. But for the most part, I gotta say, I am generally impressed and pleased with the work ethic you guys have been bringing forward and really been showing. So my only major concern at this point is that as the weather gets nice, we start to get a little senioritis, and that's going to come back to bite us pretty hard. This class is not going to lighten up. So we can't afford to go on spring break and then just never come back. Okay? We got to make sure we're mentally in the game from beginning to end. Second thing is if your parents are going to come to parent-teacher conferences, you guys are grown adults. So you guys should be there too. You guys absolutely should be there too. It's a very good practice because when you guys go to the next level, whether that's at community college, whatever it's going to be for you, your parents cannot and will not find out anything about your grades. The whole I'm paying for it argument does not work. You are a legal adult and that is your private information, and most professors will not share it. So you need to learn how to be an advocate for yourself, an advocate for your grades. Most of you do a really good job of that already, so kudos, but I think it's worthwhile that you practice that skill set. If you are uncomfortable talking to your teacher about your grades, that gives you some sense of anxiety or fear, I think that this would be a good time for you to practice that. I mean, we've been together now for a number of times, I'm not a stranger to any one of you guys, so this would be a good opportunity for us to talk and to deal with things. I view you guys as very much as young adults and not so much as students anymore. It's just more like mentees and mentor kind of relationship nowadays. Okay, so that's my bit there for us. I do also want to say that after talking with a colleague of mine, we talked yesterday about the amount of stress and pressure that everybody's under here this year. How it's been a really hard year, and that the biggest thing is students falling behind, not completing work and things like that. And while that hasn't been an issue for you all, you guys have been really good about that. We talked about the workload, and this year has been a tremendous amount of work on you guys. Now, you guys are always students who rise to the challenge, and you have done so. But keeping that in mind, Mr. Kaufman's exhausted. I know you guys are also exhausted, and we are far from being done. So what I'm going to try to do is keep that more in my mindset as we're doing things. And I don't want to say maybe backing off the pace a little bit, but providing a little bit more days like yesterday. Days like yesterday where your only task is work on your quiz. Your only task is work on your test, work on your study guide. So building a few more of those days in, so yes, it will slow down the pace a little bit, but more just taking time for us to have that in class to work on. If you're done, awesome, you can use that time wisely. If not, it provides you an opportunity for that day, for that to be your focus and not have to worry about, well, I got to get the quiz done and I got to do this and I got to do that type deal. So if those days were to happen on a Monday, Tuesday, or Thursday, or Friday, I wouldn't necessarily expect everybody to attend a live session other than for some warm-up, some review problems, so that'd be a very quick live session, like a 15, 20-minute deal. Okay? So just trying to work with you all a little bit, trying to adapt what I'm doing to benefit you guys. It's not really an issue for my class, but you guys need to be successful outside of calculus too, just as much as in, say, Mr. King's class or Ms. Litt's classes, right? So, nonetheless, it's something that I'm going to be doing as we go forward, and I think that most of you will probably appreciate a little slower of a pace. Questions? Concerns? Homework questions, then. Anything we want to talk about homework-wise?
49 on 4.3.
4.3, take a look at number 49. 4.3, look at number 49. Let me grab my book right here. Okay. Number 49. 49 on page 280. Our think about it question. Consider the function that is continuous between -5 and 5, and for which the integral from 0 to 5 is 4. We want to evaluate each of the following integrals at these values. So, what we have here is we have some function. We don't really know too much about it. We just know that it's continuous from -5 to 5. So from -5 through 5, we have some continuous function. We know right here to here that this section here has an area of 4. That's what it's telling us to begin with, yes? Okay, so when we start with part A should be pretty easy here. Part A, we're just going to split this integral into two parts, 0 to 5 for f of x dx, plus the integral 0 to 5 of 2 dx. Well, we already have this one. This is 4. This is just the horizontal line. If I graph this over here, this is the horizontal line at 2 through 5. So it gives us a nice rectangle here. And this rectangle is going to be 2 by 5, which is 10. So 4 plus 10 is 14. Some people really struggle with the whole constant being mixed in there. This is typically the way that we handle them, is we separate them. Most of the time we don't do the transformation where we bounce things up or down. We talked about that a little bit yesterday in tutoring, which we actually had some people show up for, which was nice for a change. Mr. Coughlin didn't sit there forever. The corgi made a guest appearance as he was chewing on things he wasn't supposed to. And but we talked about the pros and cons of doing, shifting our graph up this many and then reevaluating versus just keeping the graph where it is and doing the constant separately. So that's how we would approach number 1, or for 1b. Questions here or concerns here about this? I also just now realized that I never put up the answer key for this. So let's put our answer key up. Perhaps that'll help us a little bit too. That's math 2 right there. We need calculus. So I'm sure none of you would mind going back to math 2 at this point. Oh, that's not correct. Here we go. And we need the homework right here. We're looking at number 49 right here, correct? So of course you can see that's what I've done here. I'll zoom in for you guys too. So you can see that's what I've done here for A. I'm trying to just model the same work that we have going on there for A. Okay, now for the following parts, what we're going to do is we are going to use the transformations to help us a little bit. So I'm going to look at part B here. When I look at part B, I have this integral going for B from -2 to 3. -2 to 3, which is the whole function, this function, shifted back 2. So running from -2 to 3 from here to here, right? So I've taken the whole thing, I've moved it backwards 2, yes? So what I could do here is I could rewrite this function. So that way it is the original function just shifted to the left 2. So what would that look like for us? Well, that would be 0 to 5 of f of x. And this would be plus 2. And here for dx. Are we okay with this? So since the function has been shifted left 2, what we can do is we can continue to move this over. This doesn't really affect the area that's going to be happening here because we're just moving the function left and right. We're not changing it up and down, right? We haven't changed it vertically. The width here is still the same, right? So the width here originally 0 to 5 is 5. The width here from -2 to 3 is going to be 5, right? And if all I'm doing is moving it backwards a few, it's still going to be an overall distance of 4, an area here of 4. It doesn't matter whether it's behind or in front of the y-axis. That's not relevant to us being positive negative. That has to do with whether we're above or below. So looking at this, we still have an area of 4 because we're still going off of this one right here. Does that make sense on how I manipulated that, how we're thinking our way through this? Horizontal transformations will not be that big of an impact on our integrals and on our areas. Vertical transformations, movements up and down, absolutely. Horizontal left and right isn't going to change the amount of distance between the graph and the y and the x-axis. Whether that's in front of the y-axis or behind the y-axis or over the y-axis, it doesn't matter. It hasn't moved vertically, so that distance height-wise has not changed. Does that make sense? Okay, and that's kind of how we're going to attack most of the rest of the ones here. When I look at part C, for example, where it tells me that this is an even function, that tells me a little bit about symmetry. That tells me a little bit about my symmetry, so that's what we have there because it's even. That means we are symmetrical over the y-axis. So if I tell you that this is even, then it tells me that whatever I have on the right side, I will have, of course, on the left side. So that allows me to fill this in as 4, which is, of course, then 8, right? Or 2 times the original, right? And then, of course, we look at part D where this is odd, which has a different relationship. What that means is that our function is reflected over the origin, which means that this would actually go down here and be -4, and therefore the 2 will actually cancel and be 0. So that has to do more with, do you understand even and odd more so than anything else? Questions here? Believe it or not, these are all things that I did teach you in pre-calculus. You three for sure, Colin, you just learned this all in pre-calc. Well, this is all the way back in Unit 1 of pre-calc, though. Questions here, concerns here about 49. A good question to kind of talk about those transformations and things. Let's check on our live stream. Let's see how everybody on our live stream is doing. How's everybody on our live stream doing? Oh man, Todd Carlson talked smack to me. Their attendance question today was, if you could interview one person from history, who would it be? And he put your mom. My mom is a wonderful lady. She'll talk your ear off though, Todd. She'll just go on and on and on and on and on forever about ramblings that have no real meaning. She'll talk to you all about work and what they're doing at work, and at some point you're like, okay, Mrs. Kaufman, I gotta go. I got things I gotta do. And then she'll say, oh, okay, and then she'll just launch into another story. Okay. So today should hopefully be a little bit easier day than the past few. So today we are going to talk about the fundamental theorem of calculus. Fundamental theorem of calculus. So this is what calculus was originally designed to do. This is why Isaac Newton invented calculus here today. This is what he wanted and what he needed it to do. So we are going to be looking at our integrals, and we are going to be talking about how we can speed this up a little bit. So rather than doing the Riemann sums where we're adding up areas of rectangles or trapezoids or whatever else we want to use, what we're going to do is we're going to go back to where we talked about 4.1 with the antiderivative rules. So that's what we're going to rediscuss today, and how we can use the antiderivative to help us find this area, rather than doing all these other tricks and sums and limits and things like that, okay? So here's your homework on slide 2. Copy it down if you feel the need. Of course, you have it on canvas. Okay, so the fundamental theorem, the first fundamental theorem of calculus is very simply, if I have a function that is continuous on a closed interval, aka something I can take the integral of, or something I can integrate, and I have capital F where I have found the antiderivative, my function plus c, then what I can do is I can say the area from a to b of this function is going to be the antiderivative of b minus the antiderivative of a. Very simply, take your endpoints, plug them into the antiderivative, and subtract the two, and you will have your answer. No more area formulas, no more limits, no more summations, no more rectangles. How this works in actuality is you are taking the limit of the sum as you go to b, and you are subtracting away everything in front of a, leaving only the area from b to a as your remainder. If I draw a visual here, if this is our function, and I'm looking for b to a, what we're going to do here is we're going to take all of b, which would be from here all the way down to 0, and we are going to subtract from a, leaving only the section in question. That's what we're doing. That is, in essence, what we are doing. Does this make sense now that I tried with the visual? I'm not super great at drawing, you know this. The function, the execution of this is incredibly simple, so long as you can do the antiderivative, so long as you can integrate the problem. Let's take a look at one. So let's do the integral from 1 to 2 of x squared minus 3 dx. So the first thing I'm going to do is get the antiderivative. So fx, capital Fx. Of course, we're going to use our power rule for the first part of this, yes? I'm going to increase my exponent by 1, so this can become x to the third over 3. And then I have my constant rule, so minus 3x. Are we all okay so far? With, of course, plus c at the end. Are you okay? Are we comfortable? Okay. So here's how we typically write this. Is what we're going to do here is we're going to do f of 2. So this is going to be 2 cubed over 3 minus 3 times 2 plus c. This is going to give us 8 over 3 minus 6 plus c. And then we are going to do the antiderivative function at 1. So that's going to be 1 cubed over 3 minus 3 times 1 plus c. That gives us 1/3 minus 3 plus 4, negative 2/3 plus c. Are we okay with these two so far that I've done them? Okay. We're going to take and subtract. So this one minus that one. So 8/3 minus 6 plus c minus negative 2/3 plus c. And what's going to happen here, we'll distribute this negative through. I'm going to get 8/3 plus 2 more thirds minus 6. And these c's will cancel. Okay? So far, so good. Am I moving too quickly for anybody? Well, then we just simplify down. 10/3 minus 6. 6 is the same thing as 18 over 3. So that's going to be a final answer here of negative 8/3. Are we all comfortable with the work that we're doing here? Yes? Good? Okay, so let's talk a little bit about notation then. We don't actually do it this way all the time. Okay, so I'm going to show you how you would write this properly. All of this right here, we don't typically flush out quite like this. Okay? What you would normally do, are we all set before I erase this to show what this would look like traditionally? Just another minute? Okay, I'll give it just another minute. Swap out my black marker for a fresh black marker. It's a little bit better for those of us on camera. Okay, so how we would normally rewrite this is like so. So what we normally do, of course, we say equal to, and then we're going to write our antiderivative function, x cubed over 3 minus 3 minus 3x. But we don't put the plus c, because the c's are always going to cancel. You saw how they canceled there, right? That's always going to happen. Always going to happen. Because you're always going to have plus c, you'll distribute it through, and you'll end up with a minus c. The c's will always cancel. So we don't put c here. Instead, we put a large-ended bracket, typically, the end bracket. And what we're going to do is we're just going to keep our interval going, which is 1 to 2. This is typically the notation that you're going to see. It's just like this. Okay? And then, of course, what we'll do is in purple, where I did 2, we would do 2 cubed minus 3 times 2, all in a set of parentheses, of course, minus 1 cubed 3 minus 3 times 1, all in a set of parentheses there. And then, of course, we do whatever we need to do to solve it down and get down to negative 8/3. This is typically the formatting. This is typically the way we write our work. This is the way I'll expect you to write your work. Now, as we look at super complicated formulas, ones that are really, really challenging, yes, maybe we'll do this part separately and reduce it down separately, kind of some side work. Maybe we'll reduce this one down separately with some side work, but inevitably we're going to end up back in this kind of format anyway. What I am absolutely going to look for, I want to make sure that this is super clear to everybody, not only to you guys here, but to everybody on live stream, is I want to see this bracket with the antiderivative. That tells me that I know how to do the integral, I know the antiderivative, I know what numbers I'm supposed to put in. If we get this part right, I know that the mistake we might have made was a math error from this point. If we don't have this written, or if this is not correct, then we don't know how to do the problem. And that's a whole different issue. So I'm absolutely looking to see this written out. This is critical. Questions here? Okay then. We're going to do a lot of drilling and killing here today. As we talk about different ways that this method works and some different tricks we can pull with it. So this is, of course, our first slide. So I have right there, written in red, what I would write, what I expect you guys to write, and then my work to follow. And Mr. Kaufman made a math error somewhere along the way. Not sure where I made my math error, but oh well. Moving on. Let's try this one out. Oh, I know where I made my math error. I made my math error with the second part. Let's go ahead and let's try this. So the first thing here is to make sure we get a good antiderivative function. Make sure we get the good antiderivative set. Okay, so what are we going to do to take the integral of this? How do we use the integral? How are we going to get the antiderivative here? What steps would we want to take? I would. How would I rewrite it, Callie?
3x.
Okay, 3x to the 1/2. Do we really want this 3 in here, or do we want to move it out? Okay, so let's do both at the same time. Let's rewrite this so that it's the integral. 3 on the outside, right? 1 to 4. And x to the 1/2 dx. So I think that would be the first step that we're going to look for, is that rewrite. Now we can do our power property, right? So when we do this, equal to, we'll have our 3 times. We'll get our bracket 1 to 4. Our power property here is going to look like what? This would be x to the 3/2 divided by 2/3, or divided by 3/2, which is really 2/3, right? Now, before we go any farther, let's reduce a little bit. What's going to happen with those 3's? They'll cancel. So I'm left with 2x to the 3 over 2, 1 to 4 is what I'm going to evaluate. Questions here? Concerns here? Let's double check here now that we're on, what is it, slide 3, right? So let's go ahead, let's step through some of my work here with slide 3. Maybe it wants to pop up. So there's my first beginning. Of course, I did the x to the 1/2 rewrite. I moved my 3 out front as well. We did that in one step, but I did 2 there. We have our antiderivative there, 3 to the 2/3 x to the 3/2. I went ahead and canceled the 3's again. So we're on pace. We're exactly where we need to be. What are we going to do next? We're going to plug in our values, right? Okay, so let's plug them in. We're going to have 2 to the 4 3/2. And then we'll have minus 2, 1 to the 3/2. This one should be easy. Of course, that's just going to be minus 2, right? Remember that if you want, you can, of course, do this a little separately. If you want to do a little side work over here, this would be 2 cube root of 4 squared. Or no, other way around. Square root of 4 cubed. That gives us 2 square root 64, which is 2 times 8, which is going to be 16. Gives us 14 as our final answer. That would do. Let's double check what I have on slide 3 here. So I plug in 2 and 4, or excuse me, 4 and 1 going in. Each one are reduced down. I got 16 minus 2. I got 14. Questions here? It's way easier than doing the limit sums, isn't it? Way easier than doing a whole bunch of area formulas, isn't it? Let's try this one out. Let's go on to the next slide. Let's do little trig functions. Let's do some trig functions. Okay, let's go ahead and let's talk about this one. This one doesn't require a major rewrite or anything. We can just pick it up right where it is, 0 to pi over 4 of secant squared x dx. When we take the integral of this, what are we looking at here? Tangent of x. Okay, this is a pretty straightforward evaluation. Pi over 4 minus tangent at 0. Of course, tangent of pi over 4 is 1. Tangent of 0 is 0. So 1 minus 0 is 1. Questions here? Much quicker than doing what we had been doing. But And I want you to understand the reason why we don't just start with this is because if I don't show you the areas and the limits and the sums, you don't really know how this is working. You don't really know what this function is, I think, without doing 4.2 and 4.3 first. You don't know that we're taking and adding up a whole bunch of shapes forever and ever and ever infinitely to do this. And honestly, you cannot lose track of what this is. Just like when we talked about derivatives, we kept on every once in a while how to remind ourselves that a derivative was a limit, right? This is still a limit. It still has to meet certain criteria for us to do this. One of those, of course, is that it is continuous. It has to be continuous between 0 and pi over 4, which, when we talk about secant, when we talk about tangent, is a bit of an issue. There are points of discontinuity through secant and through tangent that we would have to be concerned with. So you do have to kind of pay attention to what you're doing. Okay? Can't lose track of that. Okay, skipping through our slide here. Everything looks good. Got the same work. Let's move on to the next slide here. What is this? Slide 5, I believe, right? No, 7, which comes way off. So, a different way of representing this right here. Can you write out this problem and solve it? Looking at our problem on slide 7, can you write out this problem and solve it? Problem number 4. Example number 4. Who can help me out with this? Colin, help out here. Okay, let's start by just getting the problem written out. What are we talking about doing here? Yep, we're going to do the integral, right? We want the area bounded, right? Between the graph and the x-axis. And the two vertical lines, 0 to 2, right? So this is the parameters we're talking about. So a standard integral, right? 0 to 2. What's our equation there, sir?
2x squared minus 3x plus 2.
Okay. What's going to be our antiderivative here, sir?
2x cubed over 3 minus 3x squared over 2.
And we are still running this from 0 to 2, correct? Okay. Let's switch over. Let's switch to this blue. Let's plug in and let's start solving down, right? I don't see anything that really reduces here, so let's go ahead. 2 to the third over 3 minus 3. 2 squared over 2 plus 2 times 2 minus 0 cubed over 3 minus 3. 0 squared all over 2 plus 2 times 0. Okay, so Colin, here's the reality is most of the time people don't bother writing all of this out because it's all going to go to 0, right? So we're going to focus mainly on this first half because we're going to get minus 0, which is just going to be nothing, right? So let's focus on the front half here. What are we going to get for our first term, middle term, last term here?
16 over 3 minus 6.
So let's double check. We got 12 over 2, which is 6. We got 4. Everything looks good. Let's put these together. 16 minus 3 is going to be minus 2 then, right? Okay, we need to put these together. What are we looking at for our grand total here? 10 over 3. Questions here? Issues here? Once again, this is where I'm really going to be spending a lot of my time and focus, make sure this is right. Because if this is right, but our answer is not, then it's a math error. We didn't add, subtract, multiply, divide correctly. And that's what it comes down to. And honestly, those are mistakes that we shouldn't be making in the first place. We are in calculus after all. But hey, you, Mr. Kaufman, makes them from time to time, as I already made one today. Okay, let's move on to our, well, first let's double check our work here with our slide. So our integral set up correctly, antiderivative looks good, evaluated correctly for 10/3. Okay, let's move on to our next slide. So our next slide is actually going to talk about the mean value theorem, but for integrals. We talked about the mean value theorem for derivatives, right? Now we're going to talk about the mean value theorem for integrals. So if we have a continuous function, f over ab, something that we can use the integral for, then there is some number that is c, such that f times c, or f of c, times b minus a. What this is inevitably saying is that this would be the average value throughout the integral. That there is some c value, some value between a and b, that when I plug it in, and I divide it by however many rectangles we would have, or whatever the distance is, that this would spit out the average value that we're talking about. It works very similar to how we talked about the mean value theorem producing what the average slope line would be, right? This is very similar, but now we're just talking kind of average area over this. What would this look like for the average of the different rectangles that we're adding up here? Now, we are going to use this formula in a number of ways. We're going to use this formula in a number of ways. We'll use this once or twice as it is right now, where you're going to just have maybe some stuff on the left side, and you need to plug in and solve for some stuff on the right side. You might have some stuff that goes in on the right side and work backwards to find the stuff on the left side. So this does often work both ways. A lot of times when you look at these types of questions, you just simply need to find what you have and what you don't have and plug in and reduce down. Okay? So let's jump into a problem with this. Looking at our next slide here, would be slide 9, I believe. Let's go into the slide 9. So find the values of c that are guaranteed by the mean value theorem for f of x, 9 over x cubed between 1 and 3. So let's set up our mean value theorem for integrals. Let's set up our mean value theorem for integrals. So I'm going to start with the generic form up here, a b fx dx f of c times b minus a. Are we all okay with just, I'm just copying it down from the last slide, right? Okay, so let's fill this in with what we have now. We have 1 to 3 as my integral, right? That's my limitations here, equal to 3 minus 1. I have my f of x function, which is 9 over x cubed dx. And if I want f of c, that would be 9 over c cubed, right? This is what we have to plug in. Is everybody okay with me plugging everything in where it needs to go? We're all comfortable. Okay, let's check in with where we're at on my slides work so far. So, we started simply by copying down the generic formula. And now we've plugged some stuff in. I went one step further on the board than what I did on my work in the slide there. I went and actually plugged that in for C. So I'm going to focus on this integral here. Okay? So we need to swap this out. We need to swap this out for its integral part, which is 1 to 3. When I do this, I'm going to probably need to rewrite this portion. I need to rewrite this portion. I'm actually going to take it and do it separately over here. When I do that, I'm looking at taking that 9 away, making this x to the negative third dx. When I apply my power property, that's going to become x to the negative second now, because we are adding 1, right? And this is all going to be divided by negative 2 from 1 to 3. So when I bring this back over here, it's looking like negative 9 over 2x squared. Is everyone okay with what I've done there? A little side work to help us out. Are we all comfortable with what I've done? Okay. So, and of course, on this side, we're going to get, 2 times 9 over c cubed. Right? Yep. Okay. So that's as far as my work is right now. We're all comfortable. In fact, I'm actually taking it a little bit farther. Just a little bit farther. So the next thing is, of course, we're going to need to evaluate some stuff. So let's do this integral on the left side. Let's do this plug in and solve down. Let's do this plug in and solve down. This one right here is going to be negative 9, 2, 3 squared minus negative 9, 2, 1 squared. And then we're going to have equal to our 9 over c cubed times 2. Let's reduce. 3 squared is 9, times 2 is 18, so this is negative 1/2. And then we have 1 times 2, of course, is 2 over negative 9. So that's going to be negative 4.5 or plus 4.5 or 4 1/2. So this is going to reduce down to be 4 on this side. All equal to 9 over c cubed times 2. Are we all okay with the work I've done thus far? We're all comfortable? Yes? Good? Maybe? Yes? No? Maybe? Good? Okay, well, we're almost at the end now. We're just going to solve like any old algebraic equation from here. Any old algebraic equation. We're going to divide the 2 over. Divide the 2 over. I'm going to grab it from here and do it up here. So that's going to give me 2 equal to 9 over c cubed. That's going to give me 2 equal to c cubed 9. That's going to give me C equal to the cube root of 9 over 2. That is my value of C. Questions here or concerns here about this one? It looks unfriendly, admittedly, but honestly, it's not really that big of a step from what we were doing. It's taking what we were just doing a minute ago, right, and setting it equal to a part of a formula on the other side. Everything on the left side is just a standard integral pretty much all the way down to here. And then it's just, okay, we'll solve out the other side now, right? Questions here? This is primarily what we use this theorem for, is typically for finding the value of C. So typically what we can do is we can take the original and we can actually just rewrite the original function. Instead of writing it like this, we move that b minus a over to the other side. So I put it out in front of the integral as 1 over b minus a, rather than the original function. So that's what you see on the next slide here when we're talking, of course, average value of a function. Mean value theorem, I mean average is mean, right? So that's what we're looking at, slide 10, is you can write this formula outright just for f of c, which is what you have on the top. Are we all comfortable here with this? Honestly, this is the way that if I'm looking for c, this is the way I'm writing it, is the one on top. Because I'd rather just have this equal to f of c from the very beginning and have this on this side. So that way I'm not constantly writing 9 over c cubed times 2, 9 over c cubed times 2, the whole freaking problem. But to each their own. To each their own. Questions? Okay, let's try another one. Can you do this one? Can you do this one? Find the average value over this interval. Can you find f of c? I don't want actually c. I don't want the actual c value. I just want what f of c would be. So it's actually a little bit easier than the previous one. Can you set up and solve this one down, please? Looking at our next slide, looking at, what is it, slide 11, I believe we're on here. Yes, slide 11 is what we're on now. I want to tell you guys here now while you work on this problem. Obviously, we're going to finish our unit tomorrow. 4.5 is the last section in this unit. I don't think we're going to do a second quiz. I don't really have one planned or scheduled at this time. We'll have to see. But I'm thinking that probably not. On Monday, we are going to review, and I'm thinking that on Monday, we might do a little different review. Are you guys familiar with Gym Kit?
No.
So Gym Kit is like Kahoot, but you can sabotage each other with different like power-ups and things like that. So there's a version of Gym Kit called Boss Battle, where you stack the class versus the teacher and see if you can beat them. So I'm thinking that maybe that's what we'll do on Monday.
You solve problems, well, we solve problems.
Uh-huh. The 18 of you versus the 1 of me. And I do mean all 18, because you guys who will be joining via live stream on Monday would still be able to sign into Gym Kit and do it that way. think if you guys beat me, I'll give you some bonus on your test.
Some donuts?
No, that's not what I said.
Bonus.
Donuts. The donuts would also.
I mean,
I wasn't sure what you
I'll
said. You would do it instead.
maybe not instead.
Hey, we'll leave it up to a class vote whether it be donuts or donuts. Some of your classmates don't eat donuts.
This one does. This one does.
All right, let's take another minute or so. Let's finish up, and then let's see how we did. Take another minute or so. Let's finish up, and then we'll see how we did. All right, let's go ahead. Let's get after this here. First, let's get it set up properly. How do you want me to set it up?
1 over.
With the 1 over, okay? 1 over b minus a, integral a to b, fx dx equal to f of c. The average value that we're after here, right? F of c. Okay, let's plug everything in where it needs to go. Of course, b here is going to be what? 3. Try again. B here is going to be 4 minus 1, which is 3. 1 to 4. We have our function here. Our function is 3x squared minus 2x, right? Dx all equal to f of c. So yes, 1/3 here, right? Let's do the antiderivative here. 1 to 4. What are we going to have going on? We're going to get 3x cubed over 3, right? So what's going to happen with the 3's? Of course, they're going to cancel down. So I'm actually just going to go ahead and write it as x cubed. And then what's going to happen here? Minus x squared. Same thing, the 2 and the 2 multiplier cancel, right? All this, of course, still equal to f of c. Let's plug in, let's evaluate. 1/3 times. We're going to have 4 cubed minus 4 squared minus 1 cubed minus 1 squared. Well, this second part is pretty easy because that goes to 0, yeah? So we're really just focusing on the first part here. I got 1/3 times, what is that going to be? 64 minus 16, right? What is 64 minus 16? 48. 48 times 1/3 is? So the average value here is 16.
So we can do it either way, right?
Wait a minute.
Yeah, I did it.
Like, we can use the mean value theorem to do it this way.
This is the mean value theorem. I just rewrote it a little differently. That's what I was talking about on the last slide. This is the same theorem. Mean value, average value, mean and average are synonymous, right?
Do we need to write like that on our testing quiz?
I mean, it's up to you. If I'm looking for F of C, this is the way I'm writing it because I'd rather just have it all set to F of C from the very beginning. Plus, there's times, Callie, where if I'm doing this integral, if I got a multiplier that comes out, we'll say like a 9. If a 9 would have came out here, that would have helped reduce this fraction on the outside. So that's typically why I set it up this way, if that's what I'm looking for. And 9 times out of 10, this is what we're looking for. It's pretty uncommon that I would ask you to find like B or A. I can't ask you to do both, but I could ask you to do one if I provided the rest of the information. It wouldn't be friendly, but it would be something that you could, in theory, do. Questions here about this? Let's double check my work up here on the slide. Everything looks good. Solve down, reduce, and I've got 16 as well. Let's move on to the next slide. Let's move on to another problem. So our next slide, well, go ahead and try this one out. Go ahead and try this one out. See how far along we can get here.
Huh?
I don't particularly care for it now. Okay, what are we going to do? Take the 4 out. Sounds like a good plan to me. Take the 4 out. When I take the 4 out, I've got 1/2, and then I've got 4, so that's going to make a clean 2 out in front of my integral, right? 1 to 3. What am I going to do with what's left? With the x squared plus 1 over x squared dx. Split it up into what? How would I split it?
Squared over x squared. And plus 1 over x squared.
I think this looks pretty good. That'll become 1, right? And 1 plus x squared, well, negative squared, right? dx. So I think this is going to be a lot easier to integrate than maybe leaving it as one combined fraction. So let's do the integral. We have 2 times our integral from 1 to 3. That's going to become x, and that's going to become plus negative x to the negative 1, or minus 1 over x. Are we all okay with this so far? Let's double check where we're at with our slide then. Let's double check where we're at. So first, of course, we got the same 2 multiplier out in front. Split it up, I think, is the best way to do this. I think that's the best way to handle this problem. And then we integrate from there. And from here, it's all just work now. It's all just simplify. We're now 2 times 3 minus 1 over 3 minus 1 minus 1 over 1. So all of that back half goes away again. And I'm left with 2 times 8 over 3, which is going to be 16 over 3 is my answer. Is that what you all got? What I got. Questions here, concerns here, issues here. Okay, so this isn't the only part of this question. There's a secondary part of this question. We want the average value, which we have now, the 16 over 3, and the values of x, which give us this, right? So now we do actually want C here from this value. So let's go ahead. Let's pick this up from that point. We're going to take our original function, our 4x squared plus 1 all over x squared equal to 16 over 3. I'm going to cross multiply. 12x squared plus 1 equal to 16x squared. I'll go ahead, I'll distribute 12x squared plus 12 equal to 16x squared. This is going to give us here negative 4x squared plus 12 equal to 0. I'll factor out my negative 4, and that's going to give me x squared minus 3 equal to 0. Are we all okay with the work I've done thus far? I know I'm doing a little bit quickly here, but it's just algebra. We'll set this equal to 0, x squared minus 3 equals 0, and I've got x squared equal to plus or minus the root 3. Plus or minus the root 3. Now, out of those two, which one is actually my answer? The plus root or the minus root? The plus root, the minus root is not in the integral that I've given, so only the positive root should be stated. I would look for you to specify that it has to be the positive root. Don't just write root 3 and leave it at that. When we see a root, we assume it has plus and minus in front of it unless we are told something different. Questions here? So what I normally get with this type of problem is this is normally like a 4 or 5, maybe even 6-point problem. Is I normally get a lot of people that stop right here and forget to do the whole second half. Even though this isn't hard to do, you just forget to do it. So do make sure you're reading carefully here with number 7. You will see problems again like it, I guarantee it. Are we all set here with this problem, Maddie? I know I'm standing in the way here. I'll move out the way. We're all set here with slide 12 before we move on. Okay. So, little investigation here for you all. Help us get prepared for tomorrow. Help us get prepared for tomorrow's lesson. Little investigation with slide 13. Can you do the integral of each of these? Once you find the integral, I want you to go backwards to its derivative. Can you do that? I really like you to focus on 1 and 2. If you can't get 1 and 2 done, that's okay. We're going to go ahead and get started with them in just a minute. This is probably where we'll pick up tomorrow if we don't get these all finished today. So, I'm going to go ahead and get started with number 1. So, number 1, we're going to go ahead and do the integral and then get the derivative. So, first we'll get the integral here. So, we'll swap this out for its integral part, 0 through x. This is going to become 2t squared plus 3t. 2t squared plus 3t. We can show our work if we need to, but take my word for it, we're a little crunched on time. So I need to finish the integral here. Well, that should be easy because it's just going to become 2x squared plus 3x. And then it would be minus all of this other stuff, but all of that stuff goes away, right? So this is my antiderivative. This is my integral, right? I could plug in the 0, but it's not going to give me anything, correct? Okay, so then we're taking the derivative. Derivative with respect to x. Derivative with respect to x gets us back to, when I take derivative of this, we get back to 4x plus 3, correct? Okay, let's look at the next one. Let's look at the next one. So the antiderivative of sine, well, that's going to be 3 to x here. The antiderivative of sine is cosine? Negative? Well, which one is it?
Negative.
It's negative cosine. Negative cosine. Okay, now we'll evaluate again. So I'm going to get negative cosine of x. This time I do need to keep this second part. It's actually going to become plus cosine of 3, right? Because it's already negative and it's minus the second part. So are we okay here with the next part? Yes? Okay, so now we're going to do the derivative. So d dx. Okay, so derivative of cosine is negative sine, right? So negative gives me a positive sine x. And then this is a constant. It is cosine of 3 is a constant. It's a number, right? That's going to end up as plus 0, which brings me back to sine of x, right? Are we all okay so far? What do you think is going to happen with the last one? What do you think my end derivative, my end result is going to be? I'll venture a guess. It's going to be a square root. What do you think it's going to be a square root of? Not just x. It's going to be the square root of 2x plus 1. It's going to be the square root of 2x plus 1. When you take the antiderivative, of course, you'll get something that looks like this. You can do your little magical skills on it to bring it down to right here. The only difference here is it is 2 times square root 2x plus 1. 2 times square root 2x plus 1. So this is what we're going to talk about tomorrow, which is integration by substitution. Integration by substitution, meaning that I can swap out x for a different variable and reduce down. These are the things we'll talk about tomorrow. This is the second fundamental theorem of calculus, that I can actually swap from a to any particular x value, any one. I don't have to pick firm endpoints, 1 to 3, 0 to 4, something like that. I can pick 1 through x or 1 through q or 1 through r. And I can still actually do the antiderivative. I can still do the integral. There is one caveat to this, is that when you do it, you will have to, of course, multiply by the derivative of the originals. So, for example, when I look at the next slide, I look at this one here, cosine of x. When I do this one, I spit back cosine of x times 1, which is the derivative of x. Okay? When I look at the next one here, I'm going to get x squared plus 1 in my root, a simple substitution, right? The last one, I will take and substitute in, but I need to multiply by the derivative of what I'm substituting in. The derivative of what I'm going to substitute in is 5x plus 2. That's derivative is 5. So it's not just a clean substitution. I do need to multiply by the derivative of what I'm substituting in. Does this make sense now? That is why this one here has a 2 out in front, because it's substitute in, but then I also still need to multiply by the derivative of what I'm bringing in. The derivative of 2x plus 1 is 2, so I need to multiply this by 2. Same way there with the last problem there. The derivative of that is 5, so that's where the times 5 is coming from. Questions? It's actually pretty straightforward and pretty simple when you think about it. Okay? Gang, that is it for today. That is going to be it for today, and we are just about out of time. So a well-paced out day, I think. I will see us all tomorrow. Hopefully it'll be a live stream. And you guys, I recommend you guys start packing up.